Assalamualaikum. I am Nurun Nahar Mondol, and in this video I am going to present our DLD lab project for 3.1, and that is Catch or Die. Catch or Die is a game which uses this gaming board. The gaming board consists of a 8x8 red LED matrix. Light from the matrix will fall from the top to the bottom. Player will have the green LED row to catch the light using the right button or the left button. If the player can catch the light, the score will increase. If he can't, his death will increase. After 9 deaths, the game will freeze. Now let's get acquainted with the LED matrices. This is the first row of the LED matrix, and then again these are the third, fifth and seventh row, meaning these are the odd rows of the LED matrix. These are the second row of the LED matrix. Then again these are the fourth, sixth and eighth row, meaning these are the even rows of the LED matrix. For simplicity, we have kept either the even rows or the odd rows activated for a single moment. And finally, this is the player's row. First thing we had to do for this project was to generate a 3-bit random number. For generating a random number, we have used a 7493 mod 8 counter. To run the 7493 IC, we have connected the IC with a 555 timer. Let's see how it works. So, the timer works as a gaming clock and produces an oscillatory signal in its output pin 3. Then the output pin is connected with the clock B pin of the counter, and it creates a random bit. The randomness of the bit created can be varied using the pot connected with the timer. So let's see, when we vary the pot value, the randomness can be changed. So it had stopped right now, but if we decrease the value, it starts to give a random number again. The hardware implementation of the random number generation is shown here. The mod 8 counter is connected with a timer and gives a 3-bit random number, which can be seen in the LEDs. For lighting up the LEDs in LED matrix, we have used DMARC 74138. When the enable pin of the DMARC is high, the DMARC lights up the LED that the selector pin indicates. Let's see the process. When the selector pin indicates binary 0, the Y0 pin lights up. When it indicates binary 2, the Y2 pin lights up. When it indicates binary 6, the Y6 pin lights up. We have used DMARC for controlling the row LEDs. But after generating the random number, we have to make sure that first each odd row of the LED matrix are activated at the same time, and then each even row are activated. But no two odd and even row can be both activated at a single moment. For this, we have used a 7474D flip-flop. The flip-flop is connected with a timer. Let's see the process. The timer's output pin creates a signal, and the signal works as a clock pulse of the flip-flop. For each clock pulse of the timer, Q is twice high and Q bar is twice high. But when Q is high, Q bar is low. So we have connected the Q pin to the enable pin of the odd row DMARC, and we have connected the Q bar pin with the even row DMARC. That's how when odd row is activated, even row is deactivated, and vice versa. This is the hardware implementation of the 7474 IC. The IC that is labeled delay is the D flip-flop, and we can see that for each 2 pulse from the gaming clock, the Q pin is high once. After connecting the 7474D flip-flop, we have connected a 74374 flip-flop for passing a single bit from one row to another row. The process is as follows. When the D flip-flop gets a clock pulse, it passes a bit in D0 to Q0. Here, D0 is 1, but Q0 is 0. So, after getting a positive edge, D0 is passed to Q0. So, the 1 in D0 is passed to Q0 and Q0 has become 1. Now Q0 is connected to D1 and Q1 is 0. After getting a second clock pulse, D1 is passed to Q1 and Q1 becomes 1. This is how a single bit is passed. The 374 IC's clock is connected to the Q pin of 7474D flip-flop and the Q0, Q1, Q2, etc. pin are connected with the selection pin of the 74138 DMAX. This is how a bit is passed from row 1 to row 8 lead of lead matrix. This is the hardware implementation of passing the generated bits from DMAX 1 to DMAX 2. After testing all the 8 DMAXs, we have made the gaming board and then connected the board with the DMAXs. Here you can see all the 8x8 lead matrices are connected to the 8 DMAXs. The bits from the top row 1 are passing one by one to the bottom row 8 and odd row and even row are not activated at the same time. After seeing that the random bits are for passing from row 1 to row 8, we have to make sure that the player could catch the falling light. For that, player must have the ability to move the position of the activated LED from left to right. For this, we have used a 74193 up-down counter. When the up pin of the counter is given a 0 through a switch, it moves the activated LED to the right, like this. And when the down pin of the counter is given a 0 through a switch, the activated LED is shifted to the left, like this. This is how a player could control the position of the LED of his lead row. This is the hardware implementation of controlling the player LED. When the left switch is pressed, the LED of the left got activated. When the right switch is pressed, the LED of the right got activated. If neither pressed, the LED stayed still. Doing the scoring and death count, we had to make sure that the 7 segment counts up. For this, we have used 4026 7 segment display decade counter. When a positive edge of a clock is passed in the clock pin, the counter counts up and the 7 segment also counts up, like this. When the 7 segment that gives the least significant bit counts 9, the output pin of 4026, the 5 number pin, gives a pass which enables the second 4026 to count up. This is how a 2-digit number is shown. For scoring logic, we have used comparator IC 7485. If the position of the activated lead in the 8th row, which is this row, and the player's row, which is this row, matches, then the comparator will give 1 in A equal B pin. So this pin will be high, which will give a clock pulse to the 4026 and which will count up the 7 segment. So let's see the process. Now the player's row and the 8th row didn't match, so the count is 0. If the player's row matches, the count gives 1. Then again, when the player's row matches, the count gives 2. This is how the scoring logic is met. Here, only the scoring logic is implemented. When the 8th row of the lead matrix and player's row LED matches, the score goes up. For death count, if the activated lead in the 8th row, which is this row, and the player's row, which is this row, does not match the 7 segment for death count, which is this 7 segment, will count up, and when the count will exceed 9, the gaming clock will reset and the game will freeze. Let's see the process. Here, both the 8th row and player's row matches, the count is 1. If it doesn't match, the death increases. The maximum level of death is 9. And after 9 deaths, the game will freeze. That means the random bit will freeze. So the random bit are not passing and the game stops. This is the final hardware implementation of the game. When the player can catch the falling light from the 8x8 red LED matrix using the left and right button, his score will go up. But if he can't, his death will go up. After 9 deaths, the game will freeze. So we can see his scores are going up, and if he misses, his deaths are going up. And as the player had 9 deaths, the game has freezed.